The broadcast is now starting. All attendees are in listen-only mode.
Cool. All right. So, complete session one then. What we want to provide is we invited Jibo Sanyal from Oak Ridge Geographic Data Processing Lab. You'll probably know, a Geographic Information and Technology Lab, right? So, to give us a bit of a perspective, a landscape, if you will. Really credit Dan Getman on our team for saying landscape quite a bit in our plan. I really like that term. To provide us that basis for the rest of the discussion. So, Jibo, please.
Thank you, George. Good morning.
Good morning.
Morning.
So I'm Jibo. My full name is Jibonananda Sanyal, and I've gone as Jibo since I was this big. So I'm a team lead in the Geographic Information Science and Technology group. We are about 100 people now. In summer when we have students, we are about 130, 140 people. I'm the lead for the scalable and high-performance geocomputing. So we try to solve geographic problems at scale. So the outline of what I'm going to talk today, and the technology basically took away 5 minutes. I'm going to talk a little bit about big data and why we are doing big data. I'm sure this audience really does not need an introduction to that, so it might be a little bit pedantic. But then go on to talk about what we've been doing in terms of the different projects we have, in terms of the different challenges we've had with data, and what we're trying to do with them. And then a little bit about where we are going, where ORNL is going, and potentially how the landscape is changing. So we've seen all these V's. You've seen that so many times before, so I really don't want to go over them again. But the reason I put this up here is because I made a little tweak on this last night. As I was flying in, there was this guy sitting next to me, and we started talking. And the fellow asked me, "What do you do? Why are you going to Orlando?" I said, "I'm going to talk about big data." And he literally went yawn. Yet again, big data. What's the big deal? And so that made me think that here I am talking to an audience about all these lovely V's, and in some case, some time back I'd seen like 7 V's. I can't keep track of how many V's there are. But what is it about big data that we struggle with, that we're meeting here for, and how is it going? So this goes back. Oh, that looks really washed out. So this goes back to some research that we had done some time before, is to characterize how we work with data. So on the left there, we have all the different kinds of dimensionality of data. So typically it can be point data over a certain period of time, or you could have 1D, 2D, or 3D data. And then sometimes there's 2 data sets together that make a variable. For example, wind. So that would be a vector. As this is growing, as this world of unstructured or semi-structured data is growing, this paradigm of having a spatial attribute that is an inherent part of the data is becoming a little less stronger. So we have all our Twitter feeds. They could be thought of as zero-dimensional data with a very strong geolocated component, but not as structured as let's say, a 3D cube of data points. And so this block in some sense illustrates how we could look at the different techniques that we use to represent data and how they go across different dimensionalities of data, or across scalars, vectors, and tensors. And then this is the piece here. I really cannot use this mouse. This is easier. Okay. So this time piece here is actually the main part that has really ushered in this big data revolution. We are sensing our world at unprecedented rates, just because we can. I've worked in the buildings world for a little bit, and typically for a 1 degree change in temperature in a room, it takes about 20 minutes. We are sampling it at sub-second level intervals. So, and the notion there is that we can, the hope is that maybe we can capture some transients there about the dynamics of the room that we haven't done before. So, I think that's where it gets really interesting. Now, for this room here, maybe we have 2 thermostats and data is being collected at 2 locations. So we have very high temporal, the temporal aspect of this data is very high, but the spatial aspect of the dynamics in the room are very poorly captured. So, I began to think about this yesterday, and still I didn't have a very good answer to why big data. And so I began to ask, why do we care? The sources of data typically are from some kind of sensors. It could be humans with our phones in our pockets. It could be satellite observation systems. And then with that data, we have been for a while doing a lot of predictive modeling. So we take that data and we try to come up with either explanations of what we have observed, try to understand, quantify them, or then come up with some kind of predictive notion of what may happen in the future. And this is the area that's been growing rapidly. But fundamentally, for big data to work, there has to be a very clear return on investment on what we're trying to do. That could be in the form of better knowledge, savings of time, accuracy. Fundamentally, big data needs to enable. And that's the key piece that we should all focus on as we go about this. And I like to think of it as the needle and the haystack. The needle is what we're trying to find, and the haystack is this really large set of big data that we have. So my personal definition of what is big data is essentially when our conventional tools of analysis break. This could be a 300 megabyte Excel file, and I've seen people wrestle with that. That's their own personal big data situation. But the needle is the problem, the solution, the answer that we're trying to find. Big data is all about this haystack, is to come up with an architecture that lets us find that allows us to ask those right questions that can get us to finding that needle. Quicker, faster, more accurate, all those attributes. And this is where the R&D community, I believe, can help. We can help define some of these needles, and I have a couple of examples right after this. Doing better in finding the needle, so come up with better analytics. And then keep adding more data. That's what we love to do, just because we can. So here's the first example. In this era of smart grids, we are working on different kinds of things on the electric grid. For example, we are working on energy efficiency, where since that is a load profile, what we're really trying to do is on the equipment side, come up with better equipment that can lessen the load, be more energy efficient. For loads that can be moved to different times of the day, we are doing peak shaving or peak shifting. Usually 5 or 6 p.m. is when it's the most demand on the grid, and that's when all the coal-fired power plants come online. Imagine that when we all have electric vehicles and we come back home and we plug them in. That's not going to be fun. But there are ways by which we can come up with controls and algorithms, in other words, intelligence, by which we can move some of these peak effects so that we can in some sense assure a better load profile, and that has implications on the electric grid. Reliability response is something that we have started to work on, and this is about contingencies. When something happens, we need to be able to respond to it, and becomes all the more critical in a smart grid. And then there's regulation response, and this is at a couple of second level intervals, and we need to be able to react to it. Now, the challenge here is that this has to happen at individual building level, at different places around the city, around the country, around the world really. And it has to aggregate up robustly, somehow robustly, to meet grid level needs. And that's a major challenge. So we've been working in this space. This was on my desk. We had done some work on figuring out controls and algorithms, and we put them on a very tiny BeagleBone black here. And so what you're seeing here are 5 thermostats, and they are all connected over the Modbus interface, and they go into, so this is a mock-up of a rooftop, of 5 rooftop units. And what we're really doing is using the data from here coming in to come up with some kind of control decisions. And then when it triggers something, we can see lights, which basically tell us that it worked. But this rig was very useful for us in coming up with algorithms that are novel. And the reason why it's a BeagleBone Black is because it's what, $30, $35. Your typical household bill for a year is probably about $1,500 to $2,000. And whatever you do has to make sense in terms of dollars at the end of the day. So cost effectiveness is very important in this. This is another example where we have been working with Emerson technologies, and we have a Raspberry Pi here, which again is doing the same thing, is using data to actuate things. So this takes me to what goes inside this little tiny computer. So for my own calibration, are there people here who've heard of the Voltron middleware platform? So Voltron is a middleware platform that, interesting name, that comes out of the Pacific Northwest National Lab. And this is an open source piece of software based on Python. And what it really enables is the standardized interface to different kinds of devices. And then you can have, for example, the different thermostat agents here, which can talk to each other, can talk to refrigeration cases, and have a supervisory control of some kind. Look at the data and decide. So fundamentally what we're doing here is control. So one of the really cool things that we have done here for the refrigeration cases here is that typically in a commercial establishment, a refrigeration case defrosts thrice 3 to 4 times a day. If you're out, if it's the winter, if you're in Ohio, for example, in the winter, or if you're out west, humidity is so low that there's hardly any buildup of ice on the coils. So fundamentally what that means is you don't need a defrost. So with algorithms, we've come up with a way by which, without adding any new sensors, if you look at the discharge air temperature, figure out what is the temperature. So what happens is when ice builds up, the temperature begins to rise because it acts as an insulator. At a right temperature, we can dynamically trigger a defrost. And we found that in some places we can go over a week without a defrost. And that's significant energy savings. So it's these kinds of things that I'm talking about when I'm talking about the electric grid. And these kinds of things, very dynamic, have to add up to meet grid level needs. So ORNL has been working on this grid level situational awareness tool. I'm going to skip this and just talk about Eagle Eye, which is called Eagle Eye. So this started about 8 years ago in Oak Ridge, and this is real-time situational awareness of the electric grid. This looks really, I mean, my laptop has a much higher resolution. But this is real-time electric grid. Every 15 minutes it's updated, and this is an operational system. And the really nice thing about this is it's coming back into an operational / research space to Oak Ridge. So DOE took this, and as of last week, we went online where it has come back to Oak Ridge. And it shows the status of the electric grid. Now, we have to keep it operational, so that's going to be a learning curve for at least our team, because we are researchy people, and operational means a different thing. But what we are wanting to do is to have a lot of the other analytics that we have been working on ingest into this over a period of time. So every 15 minutes, number of customers out and all that. We also have NOAA feeds that pull in hurricane forecasts. So I grabbed this image last night. But what this also does is, if it were to make landfall, there are predictive models behind the scenes that figure out how many customers can potentially be out of power. And utilities use this to actually deploy people, to redeploy people in some sense, in anticipation of what may happen. It also has petroleum and gas feeds. And so this is last night, this is Orlando, and at At 11:15, there were 78 customers who were out of power. If I were to pull this up, if that power has been restored to them, it would show. Under the hood, it's mining.
So did I hear you correctly? You can actually do predictive analysis against this data?
Yes. Yes.
So given a hurricane,